Question 1, Part C, Part 1. Find the real numbers a, b and c such that 9 over x squared times 3 minus x in brackets is equivalent to ax plus b over x squared plus c over 3 minus x. Use partial fraction decomposition to find the values of a, b and c such that ax plus b over x squared plus c over 3 minus x is equivalent to 9 over x squared times 3 minus x in brackets. So starting with the left-hand side, combine the two fractions into a single fraction, and we do that by finding a common denominator. We'll multiply the numerator and the denominator of the first fraction by 3 minus x, which is the denominator of the second fraction. And then we'll multiply the numerator and the denominator of the second fraction by the denominator of the first fraction, which is x squared. So combining both of these fractions into a single fraction, we get ax plus b in brackets times 3 minus x in brackets plus c times x squared all over x squared times 3 minus x in brackets. And that's equivalent to 9 over x squared times 3 minus x in brackets. Notice the two fractions here have the same denominators. So we can equate the numerators of both fractions. That is, ax plus b in brackets times 3 minus x in brackets plus c times x squared is equivalent to 9. Now we'll use some strategic values of x to find the values of a, b and c. So I'm going to start off by letting x equals 3. And the reason for that is that it makes the value of this bracket here equal to 0. So this entire product here is equal to 0. So we have 0 plus c times 3 squared is equal to 9, and solving for c, we get c is equal to 1. Now let x equal 0. Since a times 0 is 0, and c times 0 is 0, although we've found the value of c, this term here is equal to 0. And we form the equation 3b plus 0 is equal to 9, which means b is equal to 3. And finally, let x equal 1. So we have a plus 3 in brackets times 3 minus 1 in brackets plus 1 times 1 squared, and that's equal to 9. So solving for a, we get a is equal to 1. Therefore, a equals 1, b equals 3, and c equals 1. Part 2. Find the integral of 9 over x squared times 3 minus x in brackets dx. Recall that in Part 1 we found values of a, b and c such that ax plus b over x squared plus c over 3 minus x is equivalent to 9 over x squared times 3 minus x in brackets. And that happens to be our integrand. So expressing the integrand using a sum of two fractions and the values of a, b and c that we found earlier, we have the integral of 9 over x squared times 3 minus x in brackets dx is equal to the integral of x plus 3, since a is equal to 1, and that's over x squared dx, plus the integral of 1 over 3 minus x dx. Now the first integral can be split up as a sum of two other integrals. So we have the integral of x over x squared dx plus the integral of 3 over x squared dx plus the integral of 1 over 3 minus x dx. Now the reason this is done this way is just to make the integration a little simpler and just easier to follow or understand. Now x over x squared simplifies to 1 over x. 3 over x squared can be written as 3 times the integral of x to the power of negative 2, that's using a negative index. Now 1 over 3 minus x can be written as negative 1 over 3 minus x, and then we multiply the integral by negative 1. So this plus here turns into a minus to compensate for this negative 1 in the numerator there, since a double negative gives us a positive. Now we're ready to find the integrals of these three integrands. So the integral of 1 over x dx is ln of the absolute value of x. Now the integral of 3 times x to the power of negative 2 is 3 times x to the power of negative 1, but then we need to divide by negative 1, which is why this plus here turns into a minus here. And then we subtract ln of 3 minus x, or the absolute value of 3 minus x. Don't forget to add the constant of integration c, where c is a real number. Now these two ln functions can be combined into a single ln function using a logarithm law, and we get ln of the absolute value of x over 3 minus x minus 3 over x, so that's 3 times x to the power of -1 expressed using a positive index, plus the constant c, where c is a real number.